Okay. Hi, Iraya. Hi, Deepak. And hi, Chanmin. Arun is, yeah. Good morning, Arun. No, it's already 7 o'clock. I think we should start. Okay. So, did you guys try Mahat by any chance? So, this command which I was trying last time, which it did not work. Let me try again. So, did you guys try Mahat by? Apparently, it has already created the files which we require. So, it's not letting us continue because half of the job was already done. So maybe I'll just delete this file and then see. Okay, so I'm basically trying to execute Mahat command which failed last time because of the disk space problems. Let's just see what is going on with the cluster. So do you remember that we were talking about Mahat and we were trying to deduce a recommendation of around 1 million records? Basically, given the movie preferences of various people, we were trying to give them a recommendation of which movies they should watch. They might like which movies. So we were just building that kind of recommendation based on the past, their past ratings of various movies. So are you guys with me? Can you hear me clearly? Iraya, Deepak, Arun, Tranmin, Tuhin, can you hear me clearly? Great, great, great. So this job does fail a couple of times and then tries again and then finishes it. Once it will be done, it'll write its output to the following folder, records. At the end of it, we should have a folder here, records, and then we'll have this says item based. Yeah, here this is where it will write. Okay, it has already generated some data. So this is the kind of recommendation it is generating. It generated some of those. So basically, for the user one, what are the movies? So for the user one, 805th movie, that's the index of the movie. The rating is the strong recommendation is 5.0, meaning actually all of these are 5.0, or some they might be less or more. Okay, we just have said that we want, we here we have said in this one, in this one, that okay, so we one, two, three, four, five, six, 7, 8, 9, 10. Okay, okay. So by default, if you do not specify how many recommendations you are looking for, it gives out 10 recommendations for each person. Okay. Why one, two, one, two, three, three, four, five, six, 7, 8, 9, 10. Okay, it's also 10. So for all the users, it has given out the ratings. It is also generating it right now also. Okay. So once it's done, you'll have a recommendations file containing the, so this is the user ID saying this user is having these recommendations. And what does these recommendations comprise of? A comma separated list of various movies and their uh, how much it is recommended. So this is my movie ID and this is my rating. So this is what you'll get at the end of this process. Yes, yes, yes. For each person, it has recommended the highest movie ratings. Okay. And the highest here is 5, from 0 to 5. Okay. So top 10 recommendations it has given us. Okay. And you could use similar algorithms. You could also say you want instead of 10, you can say I just want a top 5. Okay. So you'll only get this one. And those options are there while you are running the Mahat command. This command, you can specify those when you are running this command. Right, right. So Arun, the way it happens is we generally take these recommendations, because recommendations output is generally like few MBs. Okay, it's generally like few MBs, and then you can take this and put it on your web server where you are hitting the website. Like for example, at our in Mobi, when I was churning around 200 terabytes, So the end result of 200 terabytes was around 300 MB. Okay, 300 MB was the total recommended recommendations result. Okay, although 300 MB is huge if you look at it from the plain text perspective, but still it was really really small as compared to the input. And 300 handling 300 MB is not a big deal for a usual web server. But there you cannot just load everything into memory. You still have to figure out how do you make it easy. Okay, so the general idea is that you take these recommendations from here and utilize your MySQL or MS SQL, and there 300 handling 300 MB by a database is not a big deal. Okay, so onto your web server, like you might have been you working on J2E or CGI gateway or some other mechanism, say Python, or so you push your data from here to your um, so you will have one Uzi job after Mahat, which will take up this data from your HDFS and put it directly into the into a MySQL database. From there, you will serve these results to the end user. Okay, that is the general practice, and that is good enough. Or yeah, so as soon as your Mahat finishes in the same place where the Mahat is working, you can do this. And if you're using Java API, then you don't require an additional step of copying this data. So Mahat's API will give you the pointer to the object which is holding the results, and you can iterate over the results and keep on putting it into a remote server. Okay. So that is the general trend. And in case of these frequent recommendations, the way you do is you take this data, push it to a fresh new table onto your World Wide Web server, and the moment you finish your movement of the data, you rename the tables. Okay, you rename the tables so that your users are not at all impacted. So you had an old recommendation table, so you rename that table to with a date timestamp, and the new table you put it, you just rename it to the new table again, and then you flush the cache. Okay, because most of these things are cached by various web servers. So flush the cache, uh, and then you can the new recommendations will come onto the site. So that's a general practice, but that's a very very good question. So yeah, and yeah, because most of this when we are doing churning in Mahat, it is done as a batch wise process because it will require a lot of data churning, and it might take maybe if you're churning a huge data and you have a huge cluster, still it might take a few hours. Okay, depending on how big your data is. So you do all of this as a batch process, and you keep on updating your recommendation from time to time as in when your batch process finishes. Okay, yeah, so I'm hoping that okay, so it has failed cleaning up the area, which is all right, let's see the results. Is there is a change? Mhm. Okay, okay, so there is no change at all in the file. Right. So if you're using Mahat, yes, you don't have to write recommender in MapReduce exactly. So these guys have done, most of the difficult job already. Mahat guys already have done that for you. It is internally calling MapReduce, built all the logic, and then did all the magic for you. Okay. So in case you are technically inclined and you want to understand how clustering works and how does this work, that work, I mean, going through the Mahat's manual will be sufficient. Okay. Basically, Mahat's manual explains you that how do you do clustering and how do you do this, how do you do that. So most of it is done using Mahat, and Mahat makes it very very simple to do that. Okay. The other alternative to Mahat is that the MathLib kind of libraries, which provide a similar statistical and machine learning platform. All right. Yeah. So what does exactly involved in data scientist job? So data scientist job is actually build really, if you ask me, the data scientist job is to basically build these algorithms which Mahat is providing, as in improve upon these algorithms depending upon your special cases. Okay. So, but idea it in today's time, if you see, almost everybody is, you know, when they learn to use Mahat, they start calling themselves data scientist. Okay, so there's another definition of data scientist. So when they are able to take up a data and use Mahat and get the results what they were looking for, they are called data scientist. What is the person ID? So Ilya, you remember that we were actually, let me just see some. I'll show you the data. Okay. So where did we keep data? We kept data in Asgiri. Okay. Let's just go to Asgiri. So here there was ratings.csv, right? Ratings.csv. Here first column is person ID. Okay. Second column is movie ID. Third column is how much that person liked this movie. How much one liked 1193 movies. Okay. And if you see what do these mean is there is file, another file, one, it's called movie lens 1 million. So there's a website called movie lens from where we have taken these. So here if you see users.dat, na, there you see this is the person ID. If you see 32 is the person ID, it's a female, 25 age, and this. Okay. So users.dat is describing a person, while movies.dat is describing movies. If you see, so each ID, if you see here, here, you see, creatures from Black Lagoon 19. This is the ID. Right? So you can imagine that these three tables. One is movies, other is ratings and users. And movies is primary key on movie ID, and users have primary key on user ID, while ratings have a foreign key on both the things. So this will make you easier to understand this structure. All right. So that's pretty much it. Okay. So any other question before we move on to our next topic, which is Apache Spark? So Mahat recommenders are actually written in Java, most of them. Well, not most of them, all of them actually. Because uh, so internally, since it is easy to write, it is more controllable to write MapReduce in Java. You can control each and every aspect of your map reduce. So people prefer it using, whenever they are building a library, they generally build it in Java. Okay, but as a side note, when I build recommender using Mahot and all of these platforms, I used mostly Python. Okay, and I learned Python just on for this task. Okay, it took sometime like 3 4 days to pick up Python, but it was good. It was quick. So so Mahot internally is all of these algorithms are written in Java, and internally most of these tools like HBase and most of these tools are actually written internally in Java. Yes, yes, you have all the source code of all these algorithms. Okay, and these are well-known algorithms. These are well-known algorithms, and actually Mahot is open source, so you can just check out and it shows you the details of each part. And it's if somebody is technically inclined, and almost, I mean, most of the data sciences research has happened because most of these algorithms became public and open. Earlier papers were there, people were writing papers on various algorithms, but they were not giving out the code. But after Mahot came into picture, the code became available to a large set of audience, and now they are contributing in a better form. Okay, even that there was one challenge by Netflix. So Netflix threw a challenge of $1 million. Okay, and the challenge was to build exactly what I just demonstrated you. Okay, given a data on, because Netflix hosts lots of movies, so instead of so Netflix gives recommendations to the users, and the users can also rate various movies. So Netflix hosted a challenge that whosoever improves their recommender will win a $1 million prize, and that's where the most of this game started. Okay, I mean, it did not start, but it got accelerated. Lots of people started competing, and yeah. So Netflix was one of the interesting case studies, and that algorithm which Netflix used is also now included in Apache in this, and I think it is called cosine one. This cosine one is probably the one which came from Netflix. Okay, right. So now let's start with Apache Spark. Okay. Anything else before we move on to Apache Spark? Okay. So I'm assuming that everybody is good, and let's move on. Okay. So in Apache Spark, we will be discussing basically a theoretical aspect and just the general architecture, so that you get a feel of what is Apache Spark. Okay. And if you are inclined, you can go ahead and try out a couple of examples. Okay. But Apache Spark is not yet there on our cloud. Okay. So because Apache Spark was just a small topic I planned, but it became big now. So, right. So Apache Spark is a fast and general engine for large scale data processing. So we had MapReduce, in which we create our jobs and hand it over to MapReduce and wait till the MapReduce finishes, and keep on waiting for a file called underscore success in that folder where MapReduce puts the output. And for some reasons, people find out realize that MapReduce is a bit slow for basically online kind of processing. We cannot make the user wait till our MapReduce finish. Okay, so for the use cases where we have to give the real-time results, when we say real-time, it means when the user is asking for something, you give it out. Or when there's something happening, say stream of data coming in, we are processing it and putting it at various places. So can being by basic behavior of all MapReduce tasks was batch. Okay, batch in the sense that you did your code, you wrote your MapReduce, hand it over to Hadoop, and say please execute this as per your convenience. Okay, and that's a very big difference in paradigm. Generally, in most of the programs, like when you write a program, you decide like I executed this part, the value which came in the results, I gave it to this another part and did this. So that is general way of execution. While in case of MapReduce, we wrote down our logic into map and reduce, hand it over to Hadoop and said, please execute it as per your convenience. And when these files are by on top of these files. Now, so the control was not there much. Okay, control was not there. And second, first problem was that it it is mostly batch wise. Okay, so some of the researchers did a lot of job, a lot of work, and built something like Apache Spark. And it is basically you can say that 100 times faster than as per their benchmarks. It's 100 times faster than Hadoop MapReduce in memory, because it utilizes memory to a very large extent, and 10 times faster than on disk. Okay, and it builds a similar but not really like Hadoop in terms of paradigm. Okay, and and it is integrated with HDFS and yarn and other architectures. Okay, so so basically the way it has worked, the Apache Spark works is that uh, the architecture is generally like this. So it sits on the top of yarn. The way MapReduce is sitting on the top of yarn. Yarn is basically a resource allocator. Okay, where you tell that this is my logic, go on to this machine, execute this, or allocate server for this logic, and those kind of things. So yarn does that for you, while MapReduce is you convert your logic into MapReduce and it executes MapReduces using yarn. Okay, similar to MapReduce, the Spark also sits on top of yarn. Okay, and there is a standalone scheduler on which the Spark runs. Now, there are a lot of libraries which people have been developing and have developed, such as mlib. Mlib is that machine learning library. Okay, similar to Mahat. Okay, now, and there is something called Spark streaming that you can further use to handle real-time data. Okay, and then you have got Spark SQL similar to Hive SQL, which is pretty faster. And then you have got GraphX for processing the graph, such as Facebook graph and other graph similar to any other graph oriented databases. So this is the general ecosystem of Apache Spark. Now I will start with a couple of visual ideas about how does it work. So I mean the heart of Apache Spark is something called resilient distributed dataset. Okay, so resilient distributed dataset is like HDFS. Okay, it's like HDFS. The way in HDFS you have a file, when you click on a file in this viewer, the way we have clicked on the file, we do not bother on how many machine this file is allocated. Okay, like I'll show you one user called one user called sensor file. There is one user called cabin. Okay, so one of the persons in another batch was doing a project which requires around churning. Okay, so for example this, right, it is basically 17 GB file. All right, it's basically 17 GB file containing all of the data. Now HDFS made it so simple that did not have to split by yourself. Under the hood, everything is lying on multiple computers, copied everywhere. But for you, it's just a file. It's just a file. Okay. For you, it's just a HDFS file. The way you have been dealing with other files, you just deal with this big file or the small file. So most of the under the hood job is being taken care by HDFS. Similar to similar to HDFS, Spark came up with a concept called resilient distributed dataset. It is in part in memory, part in the disk, and allocated on all the servers. And generally, RDD RDD can be created on top of other data. Okay, and basically it provides you a view of the data irrespective of the sources. Okay, so your code will look at this data as a simplified access to the data. Under the hood it might be accessing multiple nodes. If one node dies, it starts allocate it start accessing other places. So these complications related to the data sharding or related to the failover is taken care by Spark. All right, so resilient data distributed data source is like a view, okay, like a window to the actual data. Okay, so your code will only be talking to RDD, while RDD internally will be doing all sorts of heavy lifting. You ask for some data from RDD will automatically figure out that on which machine internally it is kept and then give it to you. And then once RDD notices that any of the node is failing, it starts accessing the data from another nodes, similar to similar to what HDFS did for MapReduce. Okay. So RDD is just one more layer above HDFS. HDFS is more like a file, while RDD is more like a in-memory RAM. Okay, you can think of RDD as a sort of a RAM, sort of a RAM. You don't have to worry about where the RAM is storing data, or how the RAM is storing data, and how do you how is it doing the failover. Okay, so RDD you can think of that way. So whenever okay, and so RDD has got couple of interesting concepts. So say you want to access a particular logic again and again. So Arun, here I wanted to actually warn you. So you can think of RDD as a RAM, but well, in this RDD case, it is also persisted into the disk whenever it is required. Okay, so we cannot say it is just a RAM. It also pages down to the disk. Okay, okay, and when we say RDD can be persisted in memory, it means your logic did some job and it wants to access the results of this job again, or some other logic wants to access this job. So you can persist the data, persist that portion of RDD so that it can be accessible to others. Okay, instead of just being yes, yes, Arun, that's how it works. All right. So basically, RDD provides you a way, a complete abstraction from the actual nitty-gritties of where your data is. Okay, and you keep on accessing RDD as if it's there always, and you can persist your data back into RDD so that it is available to all the nodes, and it is available at later point of time also. Okay, and RDD auto recovers from node failures exactly the way HDFS recovers. And unlike HDFS, in case of HDFS, you don't have any data type per se, right? It is just, contiguous bits. I mean, contiguous array of the bytes. It's like you just dumped the file. In case of RDD, you define the data type of various key values which you are going to store in this. Okay. So disk for RDD is a single master node or on all data nodes. If all data nodes, is it? So yes, so it's your second option. So RDD in the backend can will be storing either on disk or on HDFS or on other sources, and it basically taking care of the actual data part. I mean, whether the data has backed up or not is not the duty of RDD per se, but when you are accessing when you are accessing the data nodes, in case anything fails, it looks it up. It does a failover. It, okay, it does a failover. And when you are storing data back into RDD, okay, it will be persisted for all the other nodes. Does it make sense? So you can think of RDD as a kind of index of HDFS data with the data type also. The way while we were dealing with pig, we defined data types of each one. We said this is our variable. We created a view on top of the actual one. So the way while defining our variables in pig, similarly we define the data types in while dealing with Apache Spark. So this is my actual data and this is my view which I'm creating. Okay. So probably that pig analogy might work very well, because when we describe data into it's exactly similar way the way it happens in the pig, right? You first define that this is where my actual data is, and now I loaded this data into this particular variable, right? And when I'm doing something, I'm doing on top of that particular variable. I mean, that pig analogy is far closer to what Apache Spark does. Okay. The only difference is that the only difference you will feel is that when we were doing things in pig, it was under the hood creating map and reduce for you, while when we writing logic in Apache Spark, it does not create map reduce, it right away executes using yarn. Okay, so pig basically I mean, pig is probably the most closest version of uh, your Apache Spark, right? So basically, what these guys did was they rewrote most of the MapReduce, most of this logic. So MapReduce was planned to handle far bigger data than I mean most of us will encounter. Okay, far bigger data than most of us will encounter, and therefore the whole design was done in order to simplify in order to abstract the user from such big data. Okay. So MapReduce was done in that way for far, far, far bigger data. While Apache Spark was done in order to, make a processing faster and and for practically huge data, not that bigger data. Yes, Spark is designed to use the yarn capability. All right. So, I mean, the way pig does that, you declare a variable which is, you have defined the data types, and then that variable does not load all of the data or does not load any of data. It is just a view to the actual data. Similarly, Apache Spark also let you define an RDD. What is the data type you're going to do, and where are you going to load this file into RDD, that you can also define. And the way I just defined showed you here, it says dist file equals to sc dot text file. Sc is your connection object to your Spark. Okay, so sc is Spark connection which we create, and then we say text file is this. So now it will load this text file into this variable. I mean, this is the RDD, and you also can define the data type which is there in this record by record. All right. Now, the whole concept behind Apache Spark is about two operations called transformation and action. Okay, so there are basically two kinds of operations. One is called transformation, another is called action. Okay, there is a huge difference between the two, and I'll detail you out on each of those. Okay, each element of RDD across the cluster is run through the map function. So map is just one transformation, and okay, let me just move on to the next one. This will make a lot of sense. So there is something called Spark. When you write, the way you wrote your application in the pig, saying load this data from there, apply this filter on top of the data, filter by this, and then you said group by this, and then you said finally dump, right? So similarly, Spark provides you something called Spark driver application. Spark driver application is what? Basically the one which is trying to understand the whole script you have written or whole program you have written, and then sending and connecting to the various nodes in the network which are having a handle to RDD. So there are, let's say, one, two, three, four computers which you have configured for Spark. There are slaves for the Spark master. Spark master is mostly like a Spark driver application for convenience. Okay, now Spark driver application will send the transformations to each individual machines. Okay, and each individual machines have a copy or have a reference to the RDD. Okay, and each individual machines is dealing with their section of RDD. So this distribution of RDD across machines is the duty of Apache Spark. All right. Now, your Spark driver application will say load this file into RDD. Now, that file will be loaded into the RDD across the cluster. After that, say you have written a function like some transformation, say map is one transformation. You want to capitalize all the strings, so every node will be asked to capitalize all the strings. Capitalize as in convert the text into uppercase, and here all the nodes will be capitalizing it individually in their RDD. All right, now like this. So here, don't get intimidated if you do not know, Java. All it is doing is it is saying, so in the previous screen what we did was we loaded the content into a file. or we can say lines here. Okay, let's call it lines. Okay, so in the next one, what we did was, on lines, there is an object called lines. We executed a function which basically all it did was it computed the length of each line. That's all it did. Okay. So, and what the results of all the transformation is stored back into RDD itself. Okay. RDD is, you can think of it as a small chunk of the same file allocated to each node on which you are operating. In case exactly the way you had always thought about HDFS. So every Spark application is composed of two kinds of operations. One is transformation and other is an action. Transformation is something which runs on each nodes, writes the data back onto the particular node, okay, onto that particular node, but does not finish the process. Okay. Now, so the examples of various transformations. Transformation is this: you transform the data from one form to another, and this transformation in case of Apache Spark happens on each individual node separately. Okay. Because every node is having RDD, and on top of RDD you are running these transformations. And if we are taking still the analogy between Apache Spark and Apache Pig, so whenever we say filter the data, that is a transformation. Okay. Or for each over a row. So whenever we run for each on a row is basically when we run for each in a pig, it's equivalent to a transformation. Okay. So when you look at the Apache Spark, you will be able to take a very good analogy with Pig and Spark. It is just that uh, Apache Spark is taken far ahead, and there are few things which they have come up with really brilliantly. Now, when we say map, so whatever function you are passing to the map as an argument, like a function pointer saying this is my function, execute it on all the data. Okay. So if you so so RD resilience dataset is basically a dataset of various key value pairs. It's like a set containing sets of key and values. Okay. And when we say map, when we run transformation on that set, when we run map, uh, map is not like map reduce. Okay. It is actual connotation of the map, where if you want to apply a function on an array, if you have to apply a function on an array, you used to say map. Okay. Say you have an array, you want to double the each value of an array. Okay. Or you want to square root, compute the square root of each element. In those cases, you will apply a square root function on an array, or you will run you will map square root function to an array. Okay. So similarly, map is essentially means apply this function on each element of the array. Okay. And here in Spark's context, it means that apply this function on each element of this data set which is stored in RDD. Okay. So we will be saying dataset instead of RDD because dataset is easier to pronounce. All right. So when we say map on top of a data set, it basically applies whatever your logic is. Say your logic is square root or square or cube. And when we say apply cube onto this function or map. So i- okay, so we say map function, which means apply this function on each element of this data set. Okay. Similarly, filter as in use this function to filter the records of this array. Okay. Now this array is in this data set. So say you have a huge data set, you just load it from the file, and you only want to keep the records, you want to only keep certain functions, right? Only certain elements you want to keep. In those cases, you apply this function which will return true in case you want to keep an element, and will return false in case you do not want to keep an element. Okay. So that is the job of a filter. Filter will reduce number of elements to a smaller number, and how will that filtering happen will be decided by this function which you will write. The way I wrote here, I wrote a function here, new function, and I wrote a nice function here in lambda function in Java. Similarly, you will be writing maybe in Scala or in Java or in another language, uh, filter function here. Right? So So the way we have in Apache Pig a filter by syntax, Spark also provides you a function like that. And the way we have for each, that is the function map. This map is equivalent to for each if you think about it, and filter is equivalent to your filter command of map. Then there is something called filter map. Okay, the here when we say map does not increase the number of elements in an array. Whatever elements are there, this function will be applied on top of it. All right. While fl- flat map is equivalent to similar to map, just that it can create more elements. It can create more elements, or it can also reduce an element. All right. So that is the job of flat map. So you create your function which generates more number of elements or reduces number of elements, which and that function will be run on each element of this array, and whatever output of that function comes in will form a new array. Similarly, you have a function called group by. If you remember in Pig we had group by. Similarly, here also we have group by, and when we call this group by on a dataset of key value pairs, it will return key and list of values. This is identical to your group by of Pig or any database. Okay, so all the elements of dataset containing the same key will be grouped together. All right. And number of tasks is how do you want to divide it amongst multiple machines? That is optional. The way creating number of reducers is optional. Similarly, is done. So you hope you understand that basically these functions will be run on individual nodes and store their data back onto RDD. All right. And the detail of a lot of similar function is given on this doc manual, where sample, union, intersection, distinct, group by key, reduce by key, exactly similar to what we had at Pig, okay, is available on this URL. All right. So if you can recollect what we did at Pig, so most of this is very, very similar to the Pig. We loaded a file into a variable the way we did at Pig. Then we applied transformation. Transformation can be of the form map. Map is like for each. You can think of map as like for each. Okay. So you can say analogous to for each of pick. Okay. Now, because this will confuse you if you because you have gone through the different definition of map when we were talking about map reduce. All right. A little bit different definition. Okay. Now, similar. So if you can recollect pig, then it should not be difficult for you. The only difference between pig and spark, I'm trying to make it simple as much as I can. I can try giving you trying to analogy, is that pig used to call MapReduce, which is an additional step and makes the whole process as batch wise, while Spark makes it Spark uses directly the yarn to execute these tasks and keeps you in the control and make it faster. Now, after the transformation all they did was they transformed the data at RDD or dataset into another dataset, which can be used further and did not give you the results back. Okay. The way we do dump in case of a pig we do dump and the results come back and all of these transformations are run. Similarly, actions are the one which cause the whole thing to execute. Okay. So when we say dump, store, or any other similar job where we need to summarize, where we demand the results from the whole process, those are called actions. Okay. So how many of you are able to correlate pig and spark? Arun? So just stop me. Just stop me at any point of time. Okay. Right. So I mean, basically, when studied and went through the whole architecture of Spark, I basically Spark is something which we had traditionally long back in the times of 2002, where we used to use a similar set of paradigm to run our command across the cluster. While while a thing like HDFS and MapReduce was far new. Okay. So just that Spark has absorbed a lot of new concept and has come up with really high speed. It shows that. So, but then Spark is specifically only for Hadoop. No. I mean, it is basically it is more or less agnostic of Hadoop. Okay. It Hadoop 2.0 is what we call yarn, right? So it basically requires 2.0. Gunjan? Hmm. Hmm. Yes, in that sense, you are right. So Hadoop is specifically only for Hadoop 2.0 onwards. Okay, because it won't run on top of the older version because it requires because earlier yarn and MapReduce job was actually a single task. The job of running a process, bringing data, dividing the data. I mean, not dividing the data, running the process, taking the execution back. If process fails, then handing over the same job to other. Those kind of work was coupled with MapReduce in 1.0, but then in 2.0 the whole thing was splitted up into two portions. One is the paradigm part where there is map and there is reduce and that is gain. So that remained in MapReduce, while the underlying management of resources and execution of actual processes moved to yarn, which became very generic. In this, you can execute all sorts of processes, and therefore it became possible to actually build tools like Apache Spark on top of yarn. Right. So the general trend, what I'm seeing here is that when you, when you require a huge data, when we talk about 200 terabyte of data, okay. So and you do not require a live. You don't require it. You know, you don't keep on waiting for this to happen. It can happen as a batch job. Okay. In those cases, MapReduce is still a better solution. Okay. But I need to benchmark it to actually validate my sentence. Okay. The other benefit which I see with the Apache Spark, the other benefit which I foresee is, uh, sorry, the other benefit of MapReduce which I foresee is that you cannot screw up your MapReduce. If you are writing your logic in maps and reduces, then you cannot screw it up because it doesn't give you the control of loading this, loading that, and that kind of thing. While while the the when to execute, when to map and when not to map, when to run an action, that is a kind of decision which you might have to take. So running your job on Spark, it still requires you to know about that your data is split it. Okay, it requires you to know while coding that your data is actually splitted across cluster. Okay, say for example, when we run a map here, when we run a function like uh, uh, do something. Okay, this will, the definition will get clear as I finish. Okay, so twin, I'll address this question again, and it still remains a difficult question to answer for lots of people. Okay, so let me try to answer it once more. So in case of Spark, do we need data nodes of higher RAM? Mm, Actually, Spark says that it doesn't require much of the RAM because RDD is just a symbolic view over the data. The data might actually be stored in the disk itself. Okay. So not really it requires, it loads everything into RAM. I use the concept of RAM just to explain that it it, it basically gives you a presentation of key value pair, and the way we have an address and the value in RAM. Similarly, we have key value pair in the data set. So okay, SGA is the term. Let me just look it up. SGA. Okay. In some way, you said that Spark will better suited for real-time data streaming. Yes, yes, yes. So in those cases, what happens is, I'll come back to that one quickly. Okay, Gunjan. So just give me time. We have a couple of slides for the real-time data processing also. All right. All right. So here we were talking about actions. Actions is something like it will, right now when we are running all of these operations, right, like transformations, they are running on each individual nodes, right, and they are not correlated. Say you want to sum up all the values. In the previous one, all we did was, in this example, what we did was, so let's say there was a reg- huge data set containing lot of lines. Okay, let's say the Lord of the Ring example we took. So we had lot of lines of text. And all we did in the transformation is transform that into length of the line. We created a new data set called line lengths. Line lengths essentially contains the length of each line. All right. Now, if you have to sum up the length of each or total length of the line, as simple as like doing a summation operation across finding out total number of lines in a text, in those cases you will have to get total lengths of lines from this one, from this one, from this one, and from this one, and then join them together. Right. So that is something where you need to combine the data and bring the data or bring the results from RDD back to you. You use actions. Okay. The way we use dump command, store command in pig, similarly we do this. Okay. We use actions to bring the data from RDD back to the launcher application or Spark driver application, and then after that we can again start the transformation, load another set of data onto RDD, and keep on doing it again and again. So your Spark application is always in the control. Your Spark application says to RDD, hey, load this data and run these transformation. And whenever a transformation is run, it automatically divides the data and sends your transformer to each set of data for execution. Now, and the moment you call action, you get the results. Okay, action can be of various forms. So action is also again a function, and this function has got some interesting properties. So this function is it has got really interesting properties, and I'll describe to you. Okay, so a function is basically so these actions are basically mm, basically for getting the output from your RDD. Okay, when you try to combine the records across, say for example count would require under the hood to go through the complete RDD rather than a small section. The way it happened in transformation, the transformation happened on each node on a small section. Here you need the results. Say count is like going through the whole RDD and giving the results, right? So whenever you say count on your data set, whatever you just created will give you the total number of records across all the nodes. Okay. And similarly, collect is basically combining all the results together and putting it in some file or dumping it onto the screen. Okay. And then most importantly is one function called reduce function. Reduce function is interesting one. The way I mean it is similar to the reduce in some way, but not really too much. Reduce function, you define your function and tell that hey run this function on all the nodes, on all the data. Okay. So reduce function will run on all the data in a very interesting fashion. So this function which you are passing to reduce, so here we are passing a function to the function. Okay, this is a function pointer which we pass. We similar to map we did. We said apply this function onto each element. That was in case of map. In case of reduce here, although don't get confused by this other definition of reduce. Here we are trying to say that use my function to summarize the data. Okay, and this is like our what do we call it, combiner function. If you remember combiner function in Hadoop, where your combiner function will be given two values and combiner function will return a singular value. Okay, and it takes two argument and returns one, and it is run in parallel. Okay, so So it has to be, you know, commutative and associative, similar to our combiner function. What does it mean by that? Okay, let me just take example the way we had taken earlier. So a, a commutative or associative application, I mean, I had actually made a diagram. Yeah, here it is. Right. So this function which you're passing to reduce will be executed on any two elements of this whole data set, and then will return a function, a single value, and how it combines those two values into single one will be decided by your function. Okay, so spark actions are basically for combining all the results into singular. Now let me just dive deep into an example. Say you loaded your lines from file, and these are your lines. This is an array of strings. Okay, and when we run line lengths, when we said here said on each node compute my line length. So this is what we got. All right, this is what we got. Now now the action is being executed, and this action, what is it doing is computing the sum of line lengths. Okay, so you wrote a function like this. Basically, this is your reduce function. Okay, reduce function is taking two values, summing them up and returning it. Okay, how is this happening? How is the ठीक है, reduce, okay, and sum. So, okay, so okay, so how is this being applied? All right, basically I was describing, right? We write, so whenever we are doing reduce, we are applying our function on the data. Okay, so instead of taking the whole array of the value, it take two values, gives it to your function returns a single value, then that single value is again combined with other values, and then it returns the value. Okay, so it does sounds like a very very horribly slow process, but it is actually pretty fast. I'll show you this. Okay, so when here we are running, so line lengths we computed. Line lengths was a transformation operation which ran on each node, and all it did was for each of these values computed the line lengths. So the line length of this one is 11, and this one is 9, and so on. Okay, so for each element of this array we computed another array which has the length of each line. Okay, and this is what is the job of a transformer. Now you want to sum up all these lines. So for that you have written a simple function which basically sums up two values. And the way this action is going to be performed is interesting. So first thing it will do is, okay, first thing it will do is sum up these values, right? And how is it going to do that one? Now say we have got three nodes. So this is what we are trying to perform, and let me just put some question mark here. Okay. Now our function is basically summing up two values here and returning. Okay, and we call it. All right. So what we want to achieve right now is want to sum up all these values. So on node 1, node 2, node 3. We have three nodes here. Say on node 1 we have this section of lines. So line lengths will be this on that section. So when we say RDD, this is the RDD we look at it, we have got all these values in a single place. But under the hood, each node will have a separate set of data. Say for example here, node 1 is having this, while node 2 is having only Bhagwat Kumar, while node 3 is having Shashank and Anto. Okay, so these are the three sections of a single data sets running on three different nodes. Right, right, you can say that. Thank you. So basically here I wanted to demonstrate how does the reduce function is getting executed. So on first one, how will it compute the total length? So first it will do is take two variables out of it, sum it up, and make it 20 and 4. Now in the next step, it will take 20 and 4 and make it 24. Now finally you got 24 on node 1. Similarly on node 2, you will get only 14 because there is only single value. Here it will take two values, sum it up. Now when you want to sum all these three together, again when on the driver node all these values are being sent, you see in this diagram all these values came to the driver node, right? Now you got these three value on the driver node here. Now all this driver node will do is will take these values two at a time, okay, and combine together like 38, okay, and then uh, combine it with 24. So effectively you got 64, 62. Okay, so this is the distributed nature of your function. All right, so everybody got this part, how a reduce function is being executed, and how does it solve your problem. Okay, now so all it did was it took two values at a time, combined them using your function. Your function could be, say, right now we have taken an example of sum, but it could be min or it could be max. And it can be actually be this kind of function which we call root mean square value. Not root mean square value, square root of underscore. We call it the distance between 2 points, or the length of diagonal. So basically there is a property of these kind of functions. There is only limited set of functions which you can run on reduce. Okay, because say you are running something like average. Okay, average will give you a very very bad result. Average is not the function to be run as the reduce, because average will not give you an output. Can somebody tell me why? So you cannot run average kind of function in reduce. It is not associative, right? Now if you run through your mind, say we had to compute the average lengths, right? So here the results we are expecting is very different, and if you do the same thing like compute average of this and this, then whatever results comes in you try to compute here again, and you will get very horribly wrong results. Okay, so therefore, not every function can be used as reduce function, because reduce will take two values at a time and give it to your function, and your function will return the value. And therefore only the functions which are cumulative and associative can be used. Okay, and why does it do it? Because it has to execute your function on very small data in a distributed fashion, and therefore it is taking only two values at a time and running your function. Right. So what does reduce example return when using square root this one, right? So here I am telling that similar to sum, min, max, or square root. Okay. Hope I did not confuse. Now, does it make sense or should I explain further? Okay. So if you think about, say, 11 square plus 9 square, then square root. And then when you're trying to sum up with the next value, whatever you did earlier, then it will be squared and then summed up. Right. Okay. Okay. So if you do that, sum of square root, that's interesting point. That's interesting point. Let me just think about it. So no, but sum of what? My question, Tranmin, is sum is always of two values, right? Here, square root of this one will return you a singular value, right? I did not understand this part. Tranmin, help me understand. So you are saying sum of the square root, because square root will anyway return you a single value basically. Okay. Sum is always of more than a single value, right? So what you may be meaning to say is that square root of a1 square plus b1 square then plus square root of c1 square plus d1 square. Is that what you mean to say? Right, right. So if you have to compute a square root or square root of the squares of all the numbers, then that is a that is a function you can use. Okay. So the way I do is, because commutative and associative is difficult to visualize. Okay, it's difficult to visualize. What I do generally is I take three values a, b, and c, or maybe four values, and try to apply that function and figure out if no matter what order I executed my function on top of each two values, will I get the same results or will I get different results? Okay, that will help you also figure out which functions you can use as reduce functions. Okay, so the if you guys have a understanding about those merge sort application or merge sort algorithms or divide and conquer strategies, everywhere we apply a comparison or max function, min function, using a in a on two elements in the whole array, and then whatever results comes we compare it with further, and keep on doing it again and again until we get the results. So breaking down the whole, so the way Spark applies your reduce function is it breaks down the whole data set into two values and apply your function on each two values. Whatever results comes out, it again applies your function on two values out of the result set, and it keeps on doing it until it reaches a single value. So can somebody quickly tell me, if you have n points in your data sets, how many times your reduce function will be called? If you have n values in the dataset, how many times will your function be executed when you say reduce function? When you say my dataset dot reduce and you pass on your function, how many times your function is going to get executed on a data set of length n. So here, how many times my sum was executed? 1, okay, this was 1, and then 2. 1, 2, okay, 3, 4, 5, 6. So total number of times it was executed was 6. Okay, it's difficult to compute. It's difficult to compute. Now let me simplify my problem. Say you have a single node. You have a single node instead of multiple nodes. Okay, and still the whole logic is being divided. How many times do you think it is going to call? No. So see, first time it will execute on n by 2 points, right? Because it has divided the whole n points into 2 to 2 pairs, right? So first time it will execute on n by 2 times. So by definition, reduce function will apply or run on 2 points on each 2 points. So first it will run on n by 2. So if I so first it will create pairs of 2, right? Because it has to execute on 2 elements. So first it will run n by 2, and the second times it will run on n by 4 times, and then n by uh, 8 times, and so on. Okay, it'll keep on doing it. So how much will that be? A by 1 minus r. So it will be close to 2n times. No, it will be n actually. You are right. So Arun is right. It will be close to n or n minus 1. Okay. So first it will be n by 2, and then out of that one it will be n by 4 times, and then it will be n by 8. Basically it will keep on forming those pairs out of the results, and then again run this. It is like a tennis tournament of singles. Okay, let two people play together, and then whatever the results come, you compare it. So if you divide it into three, so total number of matches is what I'm asking. Okay, so that way. Okay, so first time if you have n players or n records in the data set, and you have to apply a reduce function, you will have to run n by 2 matches first. Then whatever whosoever wins out of those matches, you pick up all those people and then run the same thing again. Right, it's a finite many operations, it's not that way. So Gunjan, my answer was more of an approximation. So you can say that it'll start with 1, and then it will go up to n by 2. Okay, 1, 2, then it'll be 4, and so on. All right. Hmm. Right. Great. So did everybody get what does it mean by a reduce function, and what kind of functions can be the reduce function? Should I move on? There are a few more concepts which are worth discussing. So, Tuhin, Tranmin, did you get the answer, or did I confuse you in any way? Great. Okay. Now moving on. Okay. Now when we do a lot of parallel processing, and we always felt this need even in the case of MapReduce, where we always wanted to be able to communicate between the processes which are being executed on different nodes, right? Here here when you were running your transformation or action on each individual node, you were completely agnostic about what is going on inside it, right? Now say now say you all you wanted to do is count number of times your summation operation has been executed, right? The exercise which we're doing manually, we want that, say, every time my summation operation in this case is getting executed, it should I should have a record of this one. Okay, I should have a count of this one, right? So what to do in such circumstances? If we have to do this live, as in I don't want to fiddle around with logs and find out how many times it execute. I want it live, like how many times my function has been executed on what all nodes. This is what I want to figure out. So just count I need. In those cases, there is a concept of something called a uh, you know that's an accumulator. Okay, I'll talk about accumulator, and then there is something called broadcast. Okay, now broadcast variable is like a shared cache. It's like a shared cache. We say uh, Spark, SC is Spark connection, the host name, and that is my Spark host. And then we say broadcast, and we say we give a value, we give an maybe an array or whatever we want to call. And when we do that, whenever anybody is asking for the value, okay, so it will return the right results to all the people. Okay, all the people. And at the similar time, so basically it's a very good way of sharing the variable across all the processes. Okay, across all the processes, because here some operation is being run. If it wants to find out what is going on at other places, this is a great way of communicating between these nodes. Okay, it's a great way of communicating between these nodes. So all you do is, so before you start your operation, before you start the operation, you define something called a broadcast variable. Now, it is important to note that this should be defined before you start the operation of any transformation, or any, say you are running a reduce function or you are running a map function. You should declare the broadcast before your map function, and which is actually obvious, and then you keep on reading the value from there and then keep on using it. because if you want to use your broadcast variable inside any of the map function or reduce function, you of course have to declare it before that one. All right. So so basically broadcast variables are, you can think of like a mutable variables, or you can think of them as a thread safe variables, because all of these nodes will be having running different tasks. Okay, completely isolated, different virtual machine, different RAM and different everything. If you if you if you declare a value in a RAM, because every node will be having their own copy of the data, okay, will have nothing to do with the other copies of the data. Or you can, the other way you can look at a broadcast variable is a better way, is static variables. How many of you know static variables in C? Okay, how many of you know broadcast variables? So not broadcast, static variables. So static variables are something irrespective of the function call. They are sort of a global variable, and no matter how, I mean, it is shared across the function declarations. All right. Similarly, you have these broadcast variables, and you always say broadcast this, or give me the value of a broadcast. Okay, give me a value of the broadcast. And that is how you share the variable or values across the nodes, or across the Spark application. This is Spark application, and there is a Spark driver application. Okay, so you should keep that in mind. Each node is running a Spark application. Is broadcast variable a real-time variable? Yes, it is a real-time variable. Whenever we say broadcast, there is a central cache which is updated, and when we say get me the value, it gives you the, immediately a fresh value. And this synchronization across the cluster is really a smart thing, which Spark did. This is a very smart move. So whenever you say broadcast, so immediately a copy of your array is made available to all the nodes. All right. So that is the power of having a broadcast variable. So you can use broadcast variable as a shared hash map for various kinds of small data which you need to know everywhere, and you need to update very quickly. Okay, but that does not mean that you start putting everything into broadcast. Okay, broadcast variable, you should keep it small and sweet. Okay, nothing beyond. Okay, now the next step, so this is the broadcast variable. All right. Now, the other kind of variable they have provided is the accumulator. Accumulator are, for, okay, right, right. So let us take a break. Accumulator are the examples of, say, I said how many times my counts is happening. Accumulator just send a plus or minus value which gets accumulated into a value. All right. Let's take a break now, and let's take a 10 minutes break. We'll come back at 8:50. All right. Hey guys, I'm back. Great, great. But I thought, Tuhin, you were supposed to take a big break. And great, 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 great. Okay, so we'll just start at 8:52. In the meantime, if somebody has some doubt, they can ask about the past one. I'll describe that one. Or some general question somebody's having. Great. Yes, yes. Reducer function on Spark, right? Yep. So basically, how should I describe? Okay, let me just think of another way. So, did you remember combiner function on Hadoop? So, in combiner function, basically what we were doing, summarize on the same node, right? Now, when you try to do any operation or accumulation operation, say accumulation operation is also sorting, right? Sorting or finding the fastest something. Say you want to find out fast, the biggest number out of a big array, very very big array, right? So say you have to do that. So and you don't know that how big an array is going to be, right? So the general tendency and general approach to solve such kind of problem is divide and conquer. All right. And say you have got say 10 GB numbers or 10 GB strings, and you want to just find out the biggest number out of these 10 say 10 GB numbers. Okay, 10 gigabyte of numbers you have got. You have to find the best, the biggest number out of the 10 billion number, 10 GB numbers. Now, the general strategy to solve that kind of problem is that you convert this whole problem into divide this whole problem into half and half and keep on dividing it, or you take first two numbers, then first two numbers, then you compare these two numbers, save it somewhere, then take another number, and you keep on doing this uh, you know till the end, right? And again, and at the end of the whole process you will get your highest number. Now, since why did we apply on two numbers at a time? Because because first, say we do this thing for 10 numbers, at the end of day we are going to compare two numbers only, right? Or we are going to operate upon two numbers at the time anyway. Okay, and therefore, and even if you do the computation, right? If you think about the whole scenario, you will find out that dividing into two is the most optimum operation. That is why binary tree, binary search, if you do the little bit of operation, and therefore, most of these combiner and reducer, all of them they do is they take two records at a time or two values at a time, apply your function, and then store the results of all these operations, and then again do the same thing. Okay. So that is a general way of doing things. And in general, the when do you do computation? So I was just doing some computation, right? Where I was talking about total number of operations. So total number of operations is actually n log n. Total number of operation is n log n in all these scenarios. Okay. Now, I mean that's similar to like sorting, because in sorting you take merge sort or say I mean most of these sorts, right? You do take you to two portions, and then
Divide and conquer and divide and conquer. All right. So, Tuhin, was I able to make it clear? No. Great, great. So that is a general strategy whenever you want to combine, do a combination kind of operation where your result requires operation on all of the data, say summation and average, mean, average, and all that sort of things. But the only problem with average is that you cannot use a reduce function because it will not give you the correct results. If you think about it, do an average of two numbers, then do an average of next two numbers, then do an average of both these numbers is not same as summing up the four numbers and giving dividing it by four. Okay, it's not equal to that. Okay, if you have three numbers, for example, you will sum up first two, divide by two, then sum the result with the third one, and then give. So it is not equal to that one. So here, uh, I mean, the only problem occurs with these kind of functions, right? So average. So a general question which people ask is that when you cannot use an average or say say mean, when you cannot use average in a reduce or in a combiner, what do you do? So my approach to this one is, say, first, in case of Apache Spark, you will write first aggregator or first action which will compute the total number of elements. Now rewrite a transformation which will basically divide each number by that value, by the total numbers. Now you will write a combiner which will basically sum up all of this. All right, which will basically sum up all of this. Okay, there might be little bit of floating point errors. There might be a little bit of floating point errors, but that is all right. Okay, that is all right. So basically, you divide each number by total number of elements, and then use the action aggregation action, and that is how you compute average. So all of these operations you can probably convert it into these actions and transformations. Okay, so now the next set of way is your accumulator. All right. Next set of way is your accumulator. Accumulator is also a great way of giving out values from across the RDD. So node 1, node 2, node 3, node 4. Okay. So basically, in an accumulator, only additive operations are allowed. Okay. All right. Only additive operations are allowed. Okay. And the other thing is that it will going to be associative, and the value at the end of the day should result same irrespective of which one came first. Whether, like for example, each of these accumulator basically is a big variable like accumulator here, if you see, and all people can do is append to it, nothing more than that. So it's like all of these nodes are basically appending to it. Okay, and when you are running all of these operations, you should not bother about the order of the elements in which they are coming, which is obvious because when you are appending from a distributed cluster, you cannot expect them to be in certain order. Okay, so accumulator is like accumulating values from the cluster to a central system. It's like a one way pipe. Okay, it's not reading any values from accumulator, it is just sending a value. A value they are sending can be negative, can be positive, And in certain cases, in case you want to implement your own, you can also have like append operation onto a string. Okay, so that is what an accumulator is. So that is an accumulator. So it provides you broadcast and accumulator, two kind of ways of sharing the data. Okay, accumulators are really really fast, while broadcast variables might be a little slower, because when you broadcast, when a single node is broadcasting, Spark will have to take that broadcast, replicate it to all the nodes. Okay, say you say that I want to broadcast a new value. The moment you say I want to broadcast a new value, it will basically take a copy of that one and send it across to all the nodes, and that might take a bit of time in parallel. So the way these guys are doing is really really smart, a way of doing it, because what it does is, first, the moment you say broadcast, okay, it will, on all the nodes, it will immediately inform that invalidate your broadcast. Okay, it will quickly invalidate that broadcast variable. Now whosoever is trying to read from broadcast will have to wait till the new value comes in. So it provides you a really good amount of synchronization, but not really the just in time, it's not really in just in time. Okay, because there'll be a time in communication, like this node, first node will say that, hey, I'm broadcasting a new variable, and this variable has to be copied to all machines, or there is a time lag between communication from this node to a central machine saying I'm broadcasting something, and then it is going to inform to all machines that invalidate this variable, a new variable is coming. Okay, so even that communication takes time, right? While here it is only a single direction, so whenever you just need a value, all of these nodes will keep on pumping the value to a central place. In those circumstances it is pretty fast. So broadcast variable is a blocking call. Yes, that is the way it has been implemented. S- So reading from a broadcast variable is a blocking call. And I don't know if broadcasting itself is also a blocking call, that I'm not sure. But reading from broadcasting is definitely one, as per my understanding. Okay, so this is what pretty much about Apache Spark. Okay, Apache Spark is taking inspiration. I'm not sure whether they took inspiration from a pig or not, but what I figured out that it is easy to take an analogy with respect to pig. In case of a pig, you load this data into a variable. I mean, don't load it. I mean, it's just a variable which represents the data lying somewhere, and then you apply operation on top of it, filter, group by, join, this, that, and exactly same thing you do in the Apache Spark. Okay, while pig is basically under the hood creating maps and reduce, while these guys, Apache Spark guy, they designed their own system to do exactly those kind of operations really really fast. Okay, and it provides you broadcast variables, accumulator, reduce, and map. I mean actions and transformations and those kind of things. Okay. All right. So you can think of Hadoop as just only providing you reduce and flat map. Flat map is equivalent of the Hadoop's reduce. Okay, and reduce is not really that way, but you can think of it that way, because map reduce can take more than one value, all right, and does not have to be cumulative or associative. Now that is pretty much about Apache Spark. I don't have a demo prepared because I just planned it for a quick overview on Apache Spark. All right. Now there is something called Spark streaming. Okay. Spark streaming is basically a extension of Spark itself. Okay, in I mean in Spark streaming, the key in a data set is the time on which the data is coming in. Basically, whenever we say Spark streaming, it will it is basically, I'll explain to you this way. So okay, this I take a step back in case it extends a bit. Okay, so guys, I'll have to leave at 9:30, which means I have 25 more minutes, but I will try my best. I will not skip anything. Okay, I'll make sure that you understand almost all the concepts. Okay, in case something is left, we'll discuss it tomorrow again. Let's not worry about that. Okay, but I'll have to leave at 9:30 for some personal reasons. Okay, I have my kid's birthday today, so that way. And yeah, so let me just describe what does it mean by streaming. Most of us actually find streaming means only movie streaming. Okay, now I give you an example of what I was doing at Amazon before starting it up. Thank you, Arun. Yeah, so there uh, you see the on Amazon, you see the whenever you click on a product, you see the product details, right? And these details are provided by various merchant. For each product, there are say 20 merchants, and for each product, there are these kind of similar merchants. And then there are people at Amazon who basically prepare this data, find out that this data is wrong. People keep on reporting. So there are a lot of people informing a central system that, hey, informing the central system continuously that, hey, we got a newer data, we got a newer data, we got a newer data. And whenever that happens, whenever we get a blip, we get a an information from the end user or from the merchant. They all do is put it in a central queue. There there are these blips that I have changed title and I have changed image. I don't this delete this one. So all of these changes are kept in a queue, which is available in the whole organization network wide, right? In this queue, all of these people keep on pumping information, all right, and your application will read from this queue, which is coming up at very fast pace, and process this queue. Okay, your application will read from it, okay, and will suck all of this data which is coming in for you. Okay, so when you deal with this kind of speed, when you deal with this kind of a fast paced input of data, you always break it down into intervals and then process that interval, and you try to keep intervals smaller, and then process it and then immediately give the results. So this is sort of a stream processing. Okay. So I designed a small system for Amazon, and when I realized, when I looked into open source, I found out that Apache Storm is exactly what it does exactly what I was doing for processing this kind of data. Okay. So when you have this stream, what you do is you have hundreds of machines in parallel doing the same thing over and over, because the pace at which this data is coming in, the pace at which this data is coming in may not be maybe so fast. Let's say you have say thousands or thousand queries coming in per per second. Okay, to handle thousands, based on how much processing do you need to do, you will have to use maybe 30 machines. Okay, for our case, we required more than 60 machines in parallel to process this kind of a data. Now, on each of these machines, in each of these machines, you will require a way to handle, a way to quickly summarize and quickly store the data back, and then combine the data together and give the results, right? So there are multiple approaches to solve this kind of problem, because if you just keep a single machine which will read from this queue, then there are high chances that this queue will overflood, and then you will not be able to process this data. Okay. So, and therefore you will keep two machines. If you keep two machines, how are you going to make sure that they don't conflict each other? If you keep two machines, how are you going to make sure that whatever result comes in is going to combine together to give, I mean, is going to combine together. Also, while you are dividing into two machines, you have to ensure that, I mean, they are self-sufficient in itself. Okay, they do not, step on each other's feet, saying, "I need your data also. I need your data also." So that is the way you do it. Okay, so say first 10 records will be read by the first machine, then next 10 records will be read by the second machine, and they both will finish their job and put it at a central place, and from there they will again communicate and then do some job. Okay, so sorting can be one such case, that say whatever records are coming in, all you have to do is delete the duplicates and sort them and keep in the central place. Okay. Also, when you are doing such kind of jobs, you might be reading from database, you might be reading from network, you might be doing a local churning, you might be just cleaning up the data. So these kind of tasks can be further parallelized by use of threads. Okay, so that while one thread is waiting to read from the data, other thread is processing the data, and that you can further create internal queues to do that. So these kind of operations become really complex, and therefore I designed a decent enough system for doing these kind of operations, where there are a lot of operations to be done on the same machine or multiple machines without worrying about, while taking the best use of use of the processor and read write operations. Okay, so in those circumstances you use the streaming mechanism, and for that the Apache, this Spark, the one which we have just studied, can be used very efficiently for streaming. Okay, so some people just wrote a library on top of Apache, up on top of Spark, to just solve the Spark streaming problem. And this library under the hood does a lot of things for you. First, it does is, so library provides you a D-stream kind of a abstraction, in which you keep on, D-stream is like a pipe, you keep on putting the data into it and reading from it. And under the hood, it keeps on, keeps it on the RDD, resilience distributed data set. Okay, and on this RDD, basically on the back end, the key is the timestamp, and value is your actual packet. All right, so input stream is received by Apache streaming, then it will slice it into the windows of data and then hand it over to the Spark engine. All right, and and so basically, Spark streaming provides you various kinds of functions to operate upon batches of data and then do the job. Okay, so always whenever you are handling stream data, you always operate upon a window of the data. Okay, the way I was saying that 100 record came in, 10 record went to the first machine, 10 record went to the second machine. So that is the window. Okay, so this, it is a window. So always whenever we are doing up streaming, you divide the whole data into windows and then you operate upon the windows, and that's what your Apache DStream is providing. Okay, and it generates the final stream of results in batches, so each window's result is printed out to the output. Okay, so DStream is reading data from time basis, right? Time 1, time 2, time 3, time 4, and on and so on. Okay. Now that one is created as windows of, say here, windows of length 3, starting with T1 and ending at T3, while second window starts at T3. This is just an example of what does it mean by window, right? And D stream, similar to the way we had reduce operation, right? It allows you to reduce by key and the window. We say on these records of this much timestamp, execute my function, and that makes it possible to operate upon a window, right? How small a window? Very good question, Arun. So when you are defining your window, the minimum is the 1 millisecond. Okay. So minimum is the 1 millisecond, because most of the computers is still do not support beyond a millisecond. Some of the nodes nowadays, everyone is going to nanoseconds, but most of it, they generally on the API level, they give only up to milliseconds. So you say, so D stream, one of the important properties of D stream, other than your standard RDD, other than your standard Spark, is this: operate upon a window of duration, starting point and the duration. Okay, this is uh, basically, this has to be time. Okay, so starting at every 10 minutes for a duration of that one, and there is always an overlap. There can be an overlap. It is up to you, how do you want to define your duration as well as your starting point. Okay, so it says that apply your reduce function on last 30 seconds of data, and do it every 10 seconds. Okay, so there is a overlap, right? Now, so the way we were in case of a normal system, we do by numbers, like do it on these many numbers, do it on these many. In the streaming, we always operate upon time-based data. All right, and that is the power of doing a streaming job. So how the data is received in D stream. Okay, that is how a window is computed. So whenever you are defining a D stream, you keep on putting the data in a certain format which has a timestamp associated with it. All right, and on top of it, it keeps on preparing the windows and lets you operate upon the window. All right. Yeah, I'll compare, Gunjan. That's yeah. I'll compare both of them. Okay. So Mahad guys are still yet to catch up with Spark and all of this. Okay. But their functions can be used if you just take out a library. All right. So rest of the questions I'll answer very quickly. So, okay. So Arun's question is, can't we compute by reading streams of data? You can compute, but see, Spark is anyway providing you a way to execute things on the nodes, right? And whenever you are processing streams of data, you will require hundreds of nodes in parallel. So why not take the benefit of something like RDD to handle a large score of data? See, whenever you are writing data or you are doing any operation, you will require first an event bus or a queue in which people will be writing the data to, and then you'll be reading from the data. And then while reading, you'll require multiple nodes to read from it. And therefore, it makes a complete logical sense to write directly to RDD and then operate upon the RDD in the form of windows or timestamps. So, right. So either you do it by yourself, you take the data input and then you keep on pushing it. I mean, that's what some people did, right? I mean, this is Spark streaming is done by a single guy like yours. Okay, so all they did was, I mean, it's not such a big rocket science. All they prepared a big library which handles most of these operations. Okay, and I'm sure when you see your use case, you will end up, you might end up skipping the D stream and writing your own mechanisms in place. Okay, so Spark streaming is just one use case of Spark, and it's just one Java class which helps you do stuff. All right. The whole game is about these streams. So I hope I answered your question, Arun. And Gunjan, half of your question is still unanswered. I'll answer that one. Okay. So yeah. So that's pretty much. In case you are interested in, having a look at the code, this is how it is. You create first a connection to the network. It under the hood is creating a connection to Spark using the standard library. You say you give it a name and uh, okay, and then you say that, give it a name, basically what appears here, and then you say you define a window here itself, how at what pace it is going to read the data, and then you start reading the data from the socket using which host and the port, and then you can start operating on these lines, saying line reduce by window size and those kind of things. All right. And basically, Java streaming context, when we say this, it is basically creating a stream and saying that read this data at this pace. Okay. So first step was creating a connection to the service. Second step was taking the lines, taking this lines which we have created the RDD on, basically internal RDD, and or D stream, you can say these are D streams. And then on top of this stream, we are running all sorts of functions. And then on top of that, we are again running a map. Okay. And then we are doing a aggregation and giving you output. So the idea is that we want to compute, we want to compute how many users or how many uh, okay, so we want to do a computation of word count every second. Okay, say we want to do every 1 second, we want to print out what is the word count or the word frequency. So first we created a connection. Then what we did was on the lines or each of the line, we executed a function which basically splits the line by space. Okay. And it is a flat map. A flat map is equal to your map reduce, and basically it gave you an array of words in output. Okay, it gave you an array of the words in output, which is basically the keys of the game. Now, on that array of words of for each line or for each line, all you did was you did a map, meaning putting a one after each word. So word one, word two one, word three one, and that format. Once you have done that, you will be having a big list of word and one, word two, and so on. And then once you're done, I mean, after that list is there, all you did was did a reduce by key. Reduce by key is equivalent to your reduce function, and then you say word count print. So it will print the frequency of the word every 10 seconds. Okay, and you can reduce it to 1 second. Or in case you are just interested in telling that how many words are coming per second, instead of reduce by key or anything, you could just say count, and then you get a word per second frequency, at what rate we are getting the word unique words from the game. All right. So those are the things you could do. This is just one example. Okay. So here, every 10 second, this is the window it has taken. Every 10 second, it is going to read from there and do the operation. Okay. So that's pretty much about Apache streaming. So I mean, Spark streaming. And here, most important thing to do is that you should fiddle around a bit with the D stream. D stream is a abstraction layer on top of Spark. In case that thing is not sufficing, you should build your own to solve your problems, because I foresee that not all use cases are covered with D stream. Okay, so that's pretty much about Apache D stream. Okay, Apache streaming, Spark streaming, right? And most of these operations, though it sounds like a contiguous operation, but they, at the end of day, we have to break down most of them into batches. Okay, and say you want to figure out how many users, unique users are coming per second. Okay, in those cases, you read it, find out a unique in this one, and then do a count and then print it. So those kind of operations are really, really fast at Apache Spark. All right. And also, as the time window, when you have defined your key as the, when you're putting the data into RDD and you define your key as the timestamp, most of the data which is together is generally the time proximity data which came together from the input. Okay, and therefore it made a big use case for Spark streaming. Uh, for the stream, Spark became a big use case for streaming also. All right. So this is just one use case. And yeah, for rest of the things, I think we will have to take one more session tomorrow. We have a lot of stuff left. And tomorrow also we'll discuss about the projects. And guys, I would request you one thing. You guys need to form your groups. Okay. So a group of three generally has generally worked better. All right. Either you figure out Either you figure out who you want to form group with out of all 13 members, 12 members, or I will send you the I will just form the group at random and then let you know. All right. All right. So generally, I mean, some of the people in the previous sessions have come up with their own groups, and then okay. So by tomorrow, if you can figure out, I'll just send out the email IDs of all the people, and you can drop a message on that Google group saying that you are looking for this kind of a group mate. So maybe you can form some groups by tomorrow, and we can discuss it further. All right. So if no group is formed tomorrow, then I'll find it by myself, and then at random I choose it. And the other thing is that in these projects, either you come up with a project if you are doing something interesting, okay, or I will assign some project to you. Okay, right. So not really, Arun. So in the other sections, right? In other sections, what people have done is they have come up with their own solutions, come up with their own problems, and then said, "Ki, help me doing this." So in a team of three, they figured out. I gave a there is something called Amazon Big Data Set. Okay, you should go through those big data sets. In this one, you can even on this one. Okay, on this URL you will find a lot of big data sets. Okay, or you can, if you have some project in mind yourself, you can come up with that one, because the one which I have from the industry like HP for example, that one is not really covering up many use cases. It is just covering up a very, very small use case. Okay, and therefore I have not given it to multiple people. I've just put it one person who is doing it. Okay, but the real life project is they are not in most of the real life project. I The main problem remains that what exactly is their problem. Okay. Okay, and why couldn't they solve it using their own tools? Okay, so Therefore, it makes a lot of sense to first go through these data sets in public and then come up with your own, um, you know, projects. Or I will assign couple of projects to you in case you do not come up with interesting project. All right. So guys, I'll have to take a break now, and rest of the things will continue tomorrow. All right. And it is important because I do not want to rush into things, so that is why I have, yeah. Tomorrow will be our 11th session, and th- uh, thank you all. So we'll discuss it tomorrow again. In the meantime, feel free to post on the group and see if you guys can communicate together. And I'll just drop an email introducing all of you so that you can communicate further. Thank you, Gunjan. Thank you very much. And thank you, Jimmy. Thank you, Arun. Thank you, Tuhin. Thank you, Chanmi. You too have a good day. Thank you, Raya. Okay. So we start forming the teams and then we discuss further. All right.